You see reflections literally everywhere, in a mirror, a puddle, even the back of a spoon. But have you ever really stopped to think about what's going on? It turns out this simple act of light bouncing off a surface is ruled by one single universal law, and it has some surprisingly wild consequences. So, let's dive in.
Okay, so right off the bat, let's start with a puzzle. We're told there's this fundamental law of reflection, and it's always, always true. Well, if that's the case, why can you see your face perfectly in a mirror, but when you look at the wall right next to it, you see nothing? Just a wall. What's the deal? That's the big question we're going to unravel right here.
To solve this puzzle, we've got to go back to basics. We need to understand the one simple rule that governs all reflection, everywhere. I mean, in the entire universe. It's clean, it's consistent, and it is the key to everything else we're going to talk about.
And here it is, the big one, the law of reflection. It's so simple, it's beautiful. Basically, the angle a light ray hits a surface, we call that the angle of incidence, is exactly equal to the angle it bounces off at, which is the angle of reflection. And this is true for every single ray of light. It doesn't matter if it's a perfect mirror, a bumpy old wall, or heck, even the surface of the moon. This law holds true.
So really, it all boils down to this super simple idea. Angle in equals angle out, every single time. This is the bedrock, the foundation of how reflection works. It's the one rule that never, ever breaks.
All right, so we've got our universal law down. Now, let's circle back to that wall. If the law is always working, then the difference can't be in the law itself, right? The difference has to be the surface.
And yup, that's exactly it. The one thing that decides whether you see a clear image or just light is how smooth that surface is. It really is all about the texture, right down to a microscopic level.
Okay, this chart really breaks it down for us. On one hand, you've got specular reflection. Think of a smooth mirror. All the light rays come in nice and parallel, and they bounce off nice and parallel. That order is preserved, so you get a clear image. But then you've got diffuse reflection. That's our wall. See, up close, that wall is super rough and uneven. So even though the light rays come in parallel, they each hit a surface at a different angle and scatter in a million different directions.
And right here, this is the big aha moment. The law isn't broken at all, not even a little bit. On that rough wall, every single one of those scattered rays is perfectly obeying the angle in equals angle out rule. The problem is because the surface is all bumpy, the out angles all point in completely different directions. The light gets reflected, that's why we can see the wall, but the image itself is totally scrambled. And just like that, puzzle solved.
Okay, so flat surfaces, we got them. But things get really interesting when we take that same unbreakable law and apply it to a surface that's, well, curved. This is where we get into the fun world of curved mirrors. So when it comes to curved mirrors, you've basically got two main flavors. First are concave mirrors. They're also called converging mirrors, and an easy way to remember them is that they curve inward like a cave. Their job is to gather light. Then you have convex mirrors or diverging mirrors. They do the opposite. They bulge outward and spread light out. Now, concave mirrors are awesome. Their whole job is to gather up light. Any parallel rays that hit the mirror all get reflected and aimed at a single point. We call that point the focus. And it even works in reverse. If you put a light at the focus, it'll bounce off and create a perfectly parallel beam. And here's the cool part. Where all those reflected rays actually cross over and meet, that's where you'll see a sharp image form. Okay, and then you have the diverging mirrors, which, you guessed it, do the exact opposite. They spread light out. When parallel rays hit a convex mirror, they bounce off as if they came from a focal point behind the mirror. Pay attention to those words as if and appear. The light rays don't actually meet up back there, and that's a huge clue about the kind of image you're going to see. So if you want to sound like a physicist when you talk about these images, there are really just three key things to look at. First is size. Is the image bigger, smaller, or the same? Second, orientation. Is it erect, meaning right side up, or is it inverted, totally upside down? And finally, the type. Is it a real image where light rays physically cross paths, or is it a virtual image where our brain just traces the rays back to a point where they look like they came from? Kind of like your reflection in a regular bathroom mirror. Okay, I know this can all sound a bit, abstract and physics class, but these principles are literally everywhere. So let's talk about why this matters and look at how this one simple law powers technology that we use every single day. Seriously, the applications are all over the place. That flat mirror in your bathroom? Simple specular reflection. But those giant telescopes that see distant galaxies, they use huge concave mirrors to gather up every last bit of faint light. What about the side view mirror on your car? You know, the one that says objects in mirror are closer than they appear? Yep, that's a convex mirror, giving you a wider view. Same goes for those big security mirrors in stores. It's the same law, just bent and curved to do different jobs.
So when you boil it all down, here's the big takeaway. It doesn't matter if you're looking at a blurry reflection in a pond or an astronomer is capturing a galaxy billions of light years away. The exact same elegant, simple principle, angle of incidence equals angle of reflection, is doing all the work.
And that leaves us with one last question to chew on, a little food for thought. We just learned that concave mirrors can take light and focus it all down to a single, real point where those light rays physically meet. Now, light is energy, right? So what do you think would happen if you built a massive concave mirror and used it to focus all the powerful energy from the sun onto one tiny spot? How could that incredible focus be used to power something like a solar furnace? Think about it.